My name's James Morse. I work in the kernel team at ARM, and wave at me if I start speaking too quickly. This presentation's about trying to support CPU Hotplug in KVM guests, and I'll take the kernel bits, and Salil will talk about the VMM work. So before we get into the nitty-gritty, what is this for and who wants it? It takes time to boot an operating system, so it's quicker if you're doing this a lot to pre-deploy the virtual machine and then scale them up once you know what the workload is you want to deploy. And that gives you much faster workload deployment time. You can already do this with Linux for memory, it's on ARM64, and this mechanism is for doing the same thing but with CPUs. And I've heard of Kubernetes and Kata containers wanting to do this, but I'm not really familiar with them. So there's a little bit of history and some terminology we need to agree. If you hear ARM people talking, when they say Hotplug, it's typically turning a CPU off. And that's not the same as what we're talking here, because if you turn the CPU off, you can turn it back on again and keep using it. So the terminology we've got present, online, means the thing's there, you can use it. Present is it's there, but it's not online, so you can't use it. And possible is it's not there, but it might be one day. So the version of CPU Hotplug people want is initially for making CPUs that are not present when the operating system boots present, so that we can bring them online. And from a bird's eye view, the mechanism, so this thing on the right is a screenshot from the ACPI spec. There's a register for each CPU called STA, and it's got a whole load of bits that say whether it's present, whether it's enabled, and so on. And firmware can send a notification to the operating system to say it's changed something in here, and that's the mechanism that CPU Hotplug uses to have CPUs come and go. So we might ask, isn't that easy? Doesn't x86 already support this? And my reading of the history is that x86 had physical CPU Hotplug before it had virtualization. So for virtual machines, the problems had already been solved, and they're part of an existing specification. So on ARM, there is no hardware that does any of this, and there are new problems. So what's in the ACPI spec is not quite enough for us. So I'll pick on two. New CPUs come with new caches, and they're shared with other CPUs. And the scheduler needs to know how these caches are shared in order to place tasks efficiently. And on ARM, for ACPI, that's a static table called the PPTT, and it can't be changed once the machine's booted up. None of ARM's ACPI tables consider Hotplug, because nobody's building hardware that supports it, and it's a bit of a chicken and egg problem. So we get the property that everything described in ACPI is always present. The second example is the interrupt controller. Every CPU has a gadget called the git redistributor, and those have to be found and configured during Linux's early boot. And there's a strong requirement from the IRQ chip maintainer that we're not going to bring these things online late unless there's physical hardware that needs it. So the theme of these problems is that without physical hardware, we don't know we've solved the problem properly. So adding support for a virtual machine will implicitly enable the feature on real hardware too. And once somebody builds that hardware, we'd be very upset if we found out the Red Hat installer didn't work on it, and it just panics during boot. And there was an earlier series from Salil to try and wire all this up and make it work, but it's something we really need hardware to know that we've got the spec changes and the ACPI stuff done. So are we stuck, or can we do something else? Well, the actual requirements are subtly different. So we saw this is only really for cloud orchestration. And if you take all the hardware-specific bits out of it, because it's for virtual machines, it boils down to a CPU online-offline policy, and that's something you want to control from outside the guest. But it needs to look and smell like Hotplug to the guest's user space. And for the operating system in the guest, we need to know what is present, and we need that not to change under our feet. And for a virtual machine, that's not a big problem. So what we've got is allowing the VMM to toggle the ACPI enabled bit in that STA register I showed you. And that's different to the present bit, but it's in the same place. And then changing Linux so that once it sees the CPU has become enabled, so things need to be present and enabled now, it registers it, and registering is what causes things to show up in sysfs and lets user space bring it online as if it had just been added to the system and become present. And that gives us the property that everything about the system's already described in ACPI exactly as it is today, and we don't hit any of those new problems. So this is an attempt to walk through the flow with some kind of diagram. The stuff on the top half happens once during boot, and the stuff at the bottom happens every time you enable or disable a CPU. The things in yellow are events that can be triggered by firmware, and the orange blocks something that firmware has control over. So at the top left, when Linux boots, it finds all the possible CPUs from the MADT. And because we haven't defined a way of making CPUs not present, all possible CPUs are present. And Linux will then try and bring them online via PSCI, which is ARM's firmware interface for turning CPUs on and off. And that can return an error now. So that's one of the things that gets added to support this. And Linux just tolerates that returning errors because it's always been able to do that. So next, once the ACPI interpreter is ready, it registers all the online CPUs, as well as any that it finds have become enabled during the initial scan of the ACPI namespace. So from there, at runtime, so on the left, this device check is a notification from firmware that something's changed. The operating system calls STA, it notices the enable bit's been set now, and it will call CPU register. Things show up in sysfs, you get udev events to say the CPU's arrived, and it all looks like Hotplug to user space. For removal, it's very similar, that's the bottom right. Again, there's a firmware notification to say, I want to eject this and take it away. The operating system can fail this if it can't turn the CPU off for some reason, but if it succeeds, there's an eject method that gets called, and then you can call STA again, and you see some of those bits have changed, and it all gets removed. You can go around that loop as many times as you like, and the initial ACPI bus scan is what makes things like kexec work to find CPUs that were changed as part of a previous life. Some of the implementation details that are now the VMM has to handle PSCI itself because that's suddenly got some policy, and there are changes from Oliver for KVM to make that work. Remember I said there were 3 states at the beginning, online, present, and possible. As far as user space is concerned, there's now a 4th, which is enabled. And if you work on a cloud orchestrator, please get in touch if you have code that tries to inspect the kernel's present and possible masks, because those are going to start behaving funnily. There's patches to add an enabled mask as well next to them, and if we need that, we can do that. Interestingly, this should work on any architecture that uses ACPI if it can return an error for onlining CPUs. So it might be possible to get Virtual CPU Hotplug support on those architectures as well. And there's an RFC to support all of this on the mailing list, but QEMU is where things get more complicated, so I'll hand over to Salil for that.
Hello, can you hear me? Yeah, okay, great. So hi, let me first switch on the presentation. That helps. Sure, yeah. Hi, so just to give you an update, this is kind of a follow-up presentation to what I actually did in 2020 as part of the KVM forum itself. So since then, some efforts have gone through in collaboration with ARM, and few challenges which were there earlier as part of the architecture mainly, we have devised a kind of workaround to get those things, not to touch those things, but then to be able to achieve what we want, which is kind of a virtual CPU hotplug, which looks and feels like a hotplug, right? So for the end user, it would be like a hotplug, but internally we are doing some sort of tweaking at different levels. I won't say all the levels, but certain, some in certain levels to achieve that end perspective. Oh, yeah. So I'll be going through the overview. It's like mostly I'll be taking the aligner in a motivation, what exactly prompted us to go into this path. Then I'll just, to set up a discussion, I'll just go for a brief anatomy, how in general any CPU initialization happens in case of the ARM within the QEMU and the KVM. And of course, the related component that is the interrupt controller for the ARM, which is GIC, how it initializes, what are the basic key elements which actually are in context to the current discussion we need to know before we actually proceed. Beside that, we need to get into the impediments again, which is kind of a recap to what we actually discussed as part of the first presentation in 2020. So I'll just give you a brief context. What was kind of a no-no from the ARM side and the entire world who actually did not want CPU architecture components to be tweaked or touched as part of the guest or the KVM host. Then there are certain workarounds around that, what we have devised, which I just mentioned. And then we'll immediately jump onto the QEMU, what exactly are the challenges and changes what we have done. So there are certain problems I've objectivized in terms of, say, 1, 2, 3, 4, 5 problems, which depends upon the kind of design technique what we have taken to get around with the limitations posed by the architecture at both fronts, that is the guest kernel as well as the KVM host. So yeah, so in a quick replay, the motivation is basically, as you all understand, this is much vouched feature by the cloud vendors, and they require it as part of the orchestration framework of theirs. And generally the use case is to adjust their resources, which are primarily, in our case, the CPU and the memory dynamically. And it could be based upon the usage. For example, it could be a very much dynamic scenario in which certain resources are underutilized, and then you want to pull it out from the VM, which is, say, for part of some sort of a containers or pods, as you call it as. In that case, you don't want to have that kind of vCPUs allocated to them. So that's a dynamic kind of usage. Other usage could be a long-term. For example, it could be related to business model, in which a customer starts with some sort of a small-scale businesses initially, and then basically, as it grows its business, eventually it ends up in some sort of a it acquires a higher kind of hardware which is much more capable. So it might be the case in which the end user might request more resources, which he should be allowed to take. In that case, you require a similar kind of feature to be plugged in. So the other thing is, like, one of the key requirement is the look and feel of the x86. So because the end customer who are the cloud vendors, they don't want to change their the scripts and number of other things. And of course, there's a lot of a training time with respect to these kind of things as well. So what they want to do is just whatever you get in x86, they exactly want to map into the 64. One of the examples of this is the Kata container. As I said, the basic approach for them is basically hot plug everything at the start. Why? Because they want a faster boot time, and then decide basically how many resources they want to plug in. So that's a hot plug, right? For the CPU, that is what we want. So I'll just quickly get over with the terminology. That is from the ACPI perspective. So there are 3 possible states what we see in the CPUs right now as possible, present, and enabled. And enabled is something which we have introduced very recently, but yes, I'll just discuss in the coming slides. So possible is like what is the maximum possible vCPUs that can exist within the VM in its lifetime. You cannot change that, you cannot tweak that, that's fixed once and for all. The present vCPUs is something which is present, but they need to be enabled, right? And they actually cannot be used. And this is what we are trying to expose as part of the vCPU Hotplug kind of look and feel to the guest. The other part is the enabled CPUs. That means eventually they have been enabled as part of certain action which has been done within the VMM or the QEMU. And that has resulted in some sort of handshakes between the guest and the VMM, which resulted in onlining of that particular CPU, which effectively means that some PSCI calls, which are related to power management or power state coordination in the ARM, they actually enable that vCPU, and it comes out from that low power state to the actual state, right? So the brief, and that means just to set up a quick context to the actual Hotplug. So this is without Hotplug. These are basic things which happens at 40,000 feet, I would say. Well, you create a CPU basically within the VM. So when the VM ends, basically you end up in creating some sort of a CPU object, which is nothing but a representation of a CPU within the QEMU. That is a QEMU object model, and that ends up in some sort of per CPU initialization within the QEMU, and also results in some sort of a calls to the KVM that happens during the realization phase. and that results in like some sort of a creation of the vCPU within the KVM. So there's a separate context for each vCPU which gets initialized within the KVM as well. And these are, of course, again, the per CPU vCPU context, and they also initialize some sort of per CPU features like timers, PMU, debug, etc. And of course, some sort of interrupt initialization, which are per CPU, like all the private interrupts, what we see SGIs and PPIs. And of course, in the end, you have to run that CPU because you want to use them. Then, of course, there's a KVM run call. All of this right now happens with respect to whenever the thread realization of the QEMU happens. And basically, you're up and running, but not so quick. There's a ARM gig initialization which you have to do as well. So you have to primarily, the things what we need to take care of is the base addresses what need to be initialized as part of the QEMU, and basically there are certain IO devs in the memory regions which gets initialized as part of the redistributors. That those regions are something which are which gets mapped on some sort of registers, whether they are system registers or related to a gig D or gig R or CPU interfaces inside the KVM. So what are the impediments? Let's get into that very quickly. These are a recap of the earlier presentation. So just two in broad sense, basically number of CPUs, right? I talked about the possible CPUs in the system which can exist. So basically this is a red line in terms of the CPU architecture. You just cannot manipulate with the CPUs, right? So then the question arises, how would you realize the hot plug, right? That's a question we are going to answer, right? We are trying to do some sort of I would say, creative hacks, if I can put it, as to just get around with these things. And other thing is the sizing of the VGIG or the gig. So this is again the architecture constraint which has been imposed. You just cannot reinitialize the gig or uninitialize and reinitialize certain part of the components. It has to be done in whole at the init once and for all, and that remains for the VM lifetime. And then the other part is, yeah, sure. Other part is the association, which remains like the association with the VGIG and the redistributor. So the same thing happens with the guest kernel, which is like the same kind of constraints are there in the CPUs, redistributors, and the associations. So we cannot change any of these. These are like red lines. So getting into the workarounds, it's like there's no workaround at all in case of the KVM host as well as the guest kernel. We actually have to get everything the way they are, right? So memory regions, everything gets initialized the way they are expected. The only thing we are tweaking right now is the power state. So with respect to the guest kernel, the same thing, whatever the constraints from the architecture point of view I just talked about, that will remain the same. We cannot touch that. So what we can do and what we have to do, because there's some sort of changes we have to do. So there's something like currently, because whatever gets described as part of the ACPI MADT as part of the gig CPU interface, right now, just before this change, they had to remain always present. Right now, that change is still there. I mean, CPUs will remain present always because that is a constraint, right? But then how would you make it present, or I mean, in a other sense, that how would you plug and unplug in the guest? Basically, there's another bit called as enable bit, right? That comes as part of the status. We tweak that particular bit to enable or disable that particular thing. But this was also not allowed as part of the earlier changes. So there are certain changes related to online capable bit, which has been added as part of the MADT table, which just states that whether this is allowed, whether the CPU which is coming up can be online later on after the OS has been booted. So that is a key change in the guest kernel. Okay, sure. So this is the base 3 levels. So to cut the long story short is like we fully realize the vCPUs, and we basically just toggle the present and the enable bits, and we fake all of the hot plug at the QEMU object level, and we lie to the guest about the presence of the CPUs. So that is the key. So second part is what I'm going to cover very quickly, right? So what are the challenges, what we have? the challenges is like, of course, the look and feel of the vCPU Hotplug what we have, right? We cannot change, or we cannot, we have to use the same set of interfaces. What actually that means? That means the CPU objects which are getting created as part of this, somehow we need to fit into the existing initialized components, which means that, for example, GIC has got its own CPU interface state. It gets attached to some sort of an older CPU, right? CPU object, I would say here, but that gets deleted as part of the unplug action, right? At the QEMU level, right? So we have to do some sort of a tweak basically to reattach them as part of this, the QEMU changes. So that is what we are doing. But even before the hot plug, the initialization is important, right? So the key thing is, how do we initialize the entire set of possible CPs now? So there's a key but a subtle difference. So now initially everything was being initialized, had a kind of a realization in a QEMU sense. Everything was present, was realized. Now actually we end up creating ARM CPU objects for entire possible CPUs, but only realize, that is, QEMU threads are present only for the objects which are actually plugged in, right? So the vCPUs which are not plugged in doesn't have the realization part, and they are only used for the KVM population. So once the KVM is populated with entire vCPUs, that was the requirement. If you remember, I just told you that that's a CPU, the architecture constraint. We just end up in destroying those extra CPU objects what were created as part of this initialization, right? And then we again, so these slots are empty right now, and whenever the hot plug action happens, basically we have to again bring them back and attach them and fix them in the same slots. But then we need some sort of a tweaking in the GIC. So GIC has been fully realized because that's part of the architecture constraint, right? So what we do is, there's certain updates we have to give it to the GIC as part of that hot plug action which happens, which actually ties up that CPU, which is new CPU coming up, and actually updates that GIC CPU interface, which has already been realized as part of the GIC initialization, which has to happen as part of the QEMU model, right? So this is precisely what we are doing. But there are certain impediments in this, like as part of the init access operations and the updates, there are certain things we have to take care of. I'll just quickly jump onto those. These are like some subtle changes. Say, for example, realization, right? Now we only assign the CPU states to the one. Remember, I just told the threads are only for the plugged in CPUs. So basically we need to fix in this particular state of the GIC, right? So whenever a new CPU comes into picture, KVM has got every state fixed in. It's just the QEMU model we are fixing in. So basically we attach this particular new CPU to this state, or unattach it, depending on what action is being done. Then of course, there are certain register information which we need to reinstate if you destroy the CPU object, which is peculiar to QEMU, because when you reset the CPU, for example, there's some sort of a handling we have to do in case of the QEMU. What is that reset handling? That we have to reset the GIC CPU interfaces as well, right? So whenever you get such kind of event, you have to handle that. So for that, you need some sort of a coprocessor registration. So you have to redefine those registers which are not being handled by the KVM. So those kind of things we have to reinstate. And the other part is, so it's related to the presence of the CPUs within the guest. I think I briefly discussed earlier, we are making use of the present and the enable bits. So basically present will always remain as present, but enabled is something what we can tweak in, right? And for that we have done some sort of a ACPI change. There's some sort of bit which has been introduced, which makes certain CPUs online capable. That means deferred online, right? So that means entire OS or VM has come up, and we are actually allowed to basically, as part of the QEMU actions, set these particular enable bits on and off. So we are kind of faking to the guest that something is now present, though actually as part of the QEMU object model, these are not present. So that is a bit of a contradiction with respect to the actual presence of the CPUs in the guest as well as the KVM host. So one last thing is like, eventually, okay, so you have everything in place, but there's a key problem is like compatibility across different kind of releases, so which might or might not have virtual CPU hotplug, and to be very frank, we cannot deny the presence of physical CPU hotplug in the future systems, right? And what if both of them exist in future, right? So we should be able to distinguish these three cases, and all of these are in individual, they should be able to exist. So what exactly we are doing is we are making use of the OSC call from the guest kernel, and which ends up in the VMM, that is the QEMU. We evaluate that, and eventually we give the right answer, what exactly is the compatibility. And that leads to either denying those actions happening in the user space or just happening. So there's one more change which is not part of the slide, is actually the PACI aspect, which is related to security. We also, while onlining the CPUs which are coming up, we also check whether these are actually allowed as per the policy within the QEMU. So there's a VMM policy decision which is also involved in it, and that particular gives you a deny or let that CPU be online. So that's a basic simple concept what we have tried to kind of prototype. So yeah, so the prototype code right now is present as like at these latest QEMU and the kernel repositories. You can try, they work. It's not like a perfect code, it's a prototype. I would say it's a kind of a hack, but then you would agree that there's a very thin red line between the bravery and the madness, a bug or a feature, or a hack or creativity. Let's call it a creative hack, I would say. So acknowledgements to a lot of people involved, because there was a lot of discussions. This is a work of mutual interest and have been going for the past 3 years. Thank you so much, and I can take some questions if you wish.
Is anyone going to use this if we support it?
Use it. That's it. Anything for James, maybe? Yeah. Mark has got questions, I think. Or the will. Yeah, sure, Alex. There you go.
So how long has this taken from the first initial implementation to getting to where we are now?
So to this point, you mean to say? So we, actually, I started with something like in January 2021, to be very frank, the first prototype. And it took roughly 3 months to get kernel and QEMU part both. And the patches were floated in June in 2021. But I think, of course, there were objections, which were well known because there were previous attempts as well. And then there was kind of a blank in between because things were being discussed as part of the architecture team. James did quite a good work. Jon Philip from ARM and Linaro, depending on what time we are talking, because it's a long time. So they did all that work of at the background while we were having a discussion in a common platform that is a Linaro open discussions. I think where a lot of people came in and gave their point of views. And I mean, we had different approaches as well from the ARM, especially from the kernel, thanks to everyone involved in that. So earlier so there were some impediments in those approaches. So something couldn't be realized at that time. In 2021 itself, we could have had a similar kind of solution. But then because of the changes in the standards, which were not allowed for those particular states, so we just didn't go in that area. But then some more changes, like for example, enabled and present bits, like we have to have that online capable bit, right? For that, we had to wait for the standard change again. So that took a bit of time. So it's like a small things which took time. And then eventually something we could present and say that, okay, you can use it. Yeah. So conceptually it's very simple. We are not doing anything funky except within the QEMU, because QEMU changes are disruptive. What we are doing is anti-model and anti-architecture in a lot of places. Like for example, Mark also pointed out in the patches what I shared. In terms of the architecture, there's no difference between the gig CPU interface, right, and basically the CPU itself. So basically they are together, right? So, but the QEMU changes actually assumes that while we unplug the object, CPU object from the QEM, right, we actually delete the state, right? So that state still exists partly within the gig CPU interfaces, which is already realized. So we have to reconnect from the QEMU point of view that particular state into the realized state. So, which is not very clean, but it works because it's not affecting the offloaded state of the KVM of the CPU interface. We are not touching that part. So yeah, I mean, like other than that, I mean, like there are things which, for example, the initialization of the entire possible CPUs, right? If you see, so there are certain things like certain CPUs which are unplugged, right? So we take a kind of it's again, I would say it's a kind of a deviation. So we don't deviation from the QEMU itself, because QEMU doesn't have any kind of state which is not realized, right? So you create an object that ends up in that set realized call, and that with respect to the CPU, it ends up in spawning that QEMU thread as well with respect to the initialization, what happens. But we are kind of hindering that, we are stopping that particular part. Why? Because we don't need it as part of the unplugged CPUs, because that is, and there are certain things which happens with respect to that calls, which is like the creation of the CPU and the initialization of the CPU, right? And those things, we have to do it separately just for the sake of the unplugged, right? So the things which are happening for the normal sake, we are not doing for the unplugged CPUs, but some of the things we are doing as well. So the thing what we are not doing is a KVM run. Okay, so I think, yeah, so maybe you guys can try and let us know what exactly how it looks like. But there could be, there's a disclaimer that there could be bugs definitely over there, and could be problems as well.
Okay, thank you.